So today we have two presentations, great presentations, and we have to finish by 1, so everybody gets our presenters 30 minutes. So let's get started. Our next presentation is about SMR Paul Rendon, and let him introduce himself. I'll take it over.
Okay, thanks everybody. So my name is Paul Rendon, Technical Customer Management with the Enterprise Cloud Group for Seagate Technology, and I work out of the Longmont, Colorado Design Center. And for those of you that were here for the late sessions yesterday, I just want to apologize in advance. I don't have any beer, so sorry for that. Okay, so why are we here talking about shingled magnetic recording? Everybody in the industry understands that we're trying to get to larger and larger capacity gains. There are a lot of promising technologies that are being developed today, such as hammer, pattern media, but none of those really have come to fruition yet. They haven't developed economies of scale, and SMR right now really represents the most cost-effective technology to meet the required capacity gains over the next couple of years, at least. What you'll see is that you can get 25% capacity gain without really making any other changes to the drive. So no changes to heads, no changes to media, no changes to the mechanics, no changes to the electronics. So we'll see that in a bit. So what we're going to go through today is we'll do a very quick basic refresh of SMR for those of you that are not familiar with the technology. We'll talk a little bit about Seagate's drive-managed SMR architecture. We'll go through our approach to host-aware, and then we'll give you some resources that you can use and some things to think about if you are ready to start adopting this technology. So very quickly, some basics here. So when we talk about conventional drives, right, data is written along tracks, and the width of the track is really dominated by the width of the writer. When the data is then read back from these adjacently laid down tracks on the drive, there's a little bit of inefficiency because you're reading narrower than you're writing. So what you see in the blue represents some potential capacity gain, right? Now, wouldn't it be nice if you could write at the same width that you could read? Well, that's pretty much impossible. But SMR comes up with something that's almost just as good. When you write in shingled magnetic recording, you're actually overlaying the tracks instead of laying them down adjacent to each other. You'll notice that then as you write to the drive is still written with the width of the writer, but then when the data is read back, because the tracks are overlapped, you're only leaving enough room then on the exposed track for the width of the reader. So it becomes much more efficient. And even though this isn't perfectly to scale, what you can see is that the net result is you can now pack 5 tracks in the same amount of space. If you used to have 4, and if you can do that math in your head, then you come up with about a 25% areal density gain. And that's really what it's all about. So one other thing to make mention of, though, is shingles, just like think about a roof, right, on your house. If you were to lay down every single shingle and you had a hailstorm and you had one shingle get damaged right in the center of your roof, do you want to have to rip every single shingle up in order to replace that one shingle? You do not want to have to do that. So one of the techniques that we use in SMR is we're going to group these tracks so that there's not just a single continuous group of tracks. We're going to lump these into what we call bands. So absolute worst case, if you have a random write occur to an area, to like maybe one sector within a track, the absolute worst case is you have to do a read, modify, write of only one band. You don't have to read, modify, write the entire disk. So that makes it much more manageable. So let's talk a little bit about drive managed SMR. So we mentioned bands. So you start with LBAs, and that's a logical construct, and then we group those into these bands. So the bands are a physical construct, which is required because the drive directly accesses those bands. The boundaries of where those bands lie, although there's a direct correlation to the LBAs, those boundaries are not known outside the drive. Everything about SMR at this level is transparent to the host. The host has no idea it's talking to an SMR drive. It has no idea how the tracks or the bands are laid out or configured on the drive. So the drive managed SMR, that was the first drive type that was ever developed. Seagate has now shipped over 3 million into the market. This is very mature technology. Again, the fact that it's SMR, what goes on behind the scenes to manage the fact that the tracks are overlapping, those types of things, it's completely transparent to the host, which makes the drive backwards compatible with conventional drives. So the way we achieve that is we have a large write-back disk cache that's resident on the media itself. And that's what manages autonomously the write, read, modify, write commands that we need to support these random writes that we have. So the benefits then of implementing a drive managed SMR solution is that there are no host changes that are required. The drive just works. It's been proven to be very effective, personal compute, and some enterprise applications such as cold storage and archive, which is why we're discussing it today. When you think about reads, both sequential and random, there's no performance impact. There's no difference between an SMR drive and a conventional drive. There are some corner cases, however, there's some challenges that we're going to talk about because of the fact that the tracks are overlapped and you have to accommodate this read, modify, write function for random writes. So again, we're leveraging this write-back disk cache, and when we do sequential writes, and we'll get into this in a little more detail as well, the drive will be able to detect that the host is trying to do sequential writes. It will take a little bit of data to buffer up for the drive to be able to determine that. Once that happens, then it writes around the cache and it will stream directly to the main store. So in that sense, you're not filling up the cache for data that you don't need to. And again, for those sequential writes, you're getting at least conventional performance, in some cases, even slightly better. So the challenge is, because of this technology, is that this cache is fixed and it's a limited resource. There's a trade-off that has to happen between how large of a cache that you make compared to how much areal density gain you ultimately get. So there's a sweet spot there. So based on the actual capacity we're trying to achieve, we size the cache accordingly. And that cache can vary from product to product, and it ends up becoming, there's a secret sauce that we use to size that cache. And then a note about read performance impact if reads are fragmented. If you are doing random writes and you end up with some data that is in the cache and some data that's in the memory, you could see some additional latencies if you do an immediate read back of the random data that you just wrote, because you'll be fragmented, you'll be reading partially from the cache and partially from the main store. So that can cause some latencies. So there are some corner case, what you could refer to as corner cases. There are some challenges around this technology, which is why traditionally it has not been used for really heavy random nature workloads. That's why one of the reasons it was initially deployed in the personal compute space, and it's now finding its way into some archive and cold storage applications. So the cache cleaning can be complex, because if you're randomly writing and you don't have good spatial or temporal locality in the cache, there's also some other potential latency that can happen, especially if the cache ends up getting full and you're still trying to do some random writes. The host will actually have to wait for, as the cache is cleaning itself, as it's writing back to main store. And so again, you could see some latency there because it won't be able to complete the initial command. That the host just can't simply write into a cache that's full, right? So the cache will need some idle time in order to be able to clear itself out as the drive is being used. And then the write around, the sequential write that I mentioned, there are some challenges with that as well. The drive trying to detect the host is doing a sequential stream, a long sequential stream, can be tricky. It needs a certain amount of data to be streamed before the drive understands that it is actually being streamed. The drive can get confused between, am I seeing multiple streams or am I actually seeing a random write? So it has to be able to buffer up enough data from all the streams to understand that it's actually getting multiple streams. And then long inter command time. So what we're saying here is, if you're streaming and then there's some delay before the next write happens, the drive's not sure, did you stop streaming to me, or is this temporary? Should I hold my place and then keep streaming, or do I need to flush myself and then start over again when you start streaming again? And then just an operational note, multiple tracks needed just means that as we are streaming, that we're going to make use of multiple tracks. We'll have one in the buffer while we're writing another one. So there are some best practices that you need to be aware of that we recommend when you're dealing with this technology. You have to ensure that there's a certain amount of idle time. You can't hit the drive with 100% workload all the time, especially if there are a lot of random writes involved. Eventually the cache will fill and you'll get into that situation where the host gets stalled because it's waiting for the cache to fill. It also minimizes those fragmentation conditions that I mentioned. You want to be able to do truly sequential writes. It's not always an easy thing to understand how the drive is perceiving your workload. You may think you understand your application. You may think you understand your workload. You may think that it's purely sequential. But when you look at the software stack and the interactions with the file system, you might be doing some journaling. There might be some metadata updates going on. All those kinds of things will eventually lead to random writes. And that, again, will lead into those challenges that we talked about. When you are trying to get the drive into a streaming mode, you want to be able to write with a high transfer length and deep queues. That will allow the drive to detect that you're trying to do a streaming transfer faster. And then finally, you want to limit and concentrate your random writes. You don't want to be writing randomly all around the drive. You want to limit and concentrate those, because then the cache cleaning will be more effective. And when we start talking later about things like garbage collection, it helps with that as well. So there are basically 3 drive types that are being developed right now. So you have drive managed exists today in Seagate. You've also got host managed and host aware. And there are specs going through the T10 and the T13, the SATA and the SAS committees right now, to develop command sets and protocols and configuration parameters for host aware and for host managed. So again, for drive managed, everything happens autonomously. The host doesn't even know it's talking to an SMR drive. With host managed now, we bring in the idea of additional commands and additional data constructs. And the idea with host managed is that now the SMR specifics, some of the architectural specifics are now exposed to the host, so the host can take advantage of those. A host managed device, however, is very strict. It has a certain number of commands and a certain number of configuration parameters. And if you go outside of those, like for example, we'll start talking about write pointers later. If you don't write to the write pointer during a sequential write, the drive will throw an error. And it will say, you didn't follow the standards, you didn't follow the protocols, I don't know what to do with this, you're not writing at the right pointer, and it will actually abort the command. So with host managed, you have to follow the rules. That also makes a drive that is host managed not backwards compatible. That means that if you plug it in to a host, the host needs to be aware that's talking to a host managed drive. That's the only way that the two can communicate and work. And one of the main reasons is because host managed, it requires a new device type. So when the host queries the drive, it will get a unique device type and it will say, I'm a host managed drive. With host aware, the concept here is that it's a superset of drive managed and host managed. We're taking our same drive managed technology and we are scaling it up to create this host aware device. It's still backwards compatible with conventional drives. That means that if you violate the rules, if you don't write at the right pointer, if you exceed the maximum number recommended, a certain type of zone, for example, and we'll get into that in a little bit, we don't throw an error. What we do is we will revert back to the drive managed architecture and we'll let the cache take care of some of the random functions. So you can't break the interface, you can't break the drive. The drive will always work. But it also has similarities to host managed, in that it has many of the same extensions to the ATA and SCSI command sets. It's a little bit different in that host aware has what are called write preferred zones, not mandatory write sequential zones. So a little bit of a nuance there. But basically that allows a host-aware drive to act just like a host-managed drive if the host and the application have been modified to take advantage of the fact that these drives are using these new standards. So the way we'd like to think of it is that a host-managed drive is restrictive. It has rules that you have to follow. A host-aware drive is permissive. You should follow the rules, but if you don't, we can always fall back and go into our old drive managed mode and everything will just keep working just fine. So the goals of our host-aware solution is we wanted to create true performance parity with conventional disks. We wanted to broaden the use case over drive managed. We want to be able to drive the performance up and the compatibility up to the point where we can extend SMR into additional tiers and into additional markets beyond just deep, cold storage. And we want to make the sequential detection trivial. So instead of the drive guessing when are you actually going to start doing sequentials, alarm burst, I need enough data, okay, now I believe you, now I'm going to bypass the cache. With these new command sets, the host, as long as it's writing to the write pointer, the drive will know that it's doing a sequential write and will automatically bypass the cache. And so there's a lot less overhead there and increases performance, especially of sequential writes. And then we wanted minimal interface changes. So very similar to host managed, there are no changes to read and write commands. Host-aware, host managed do not change the actual read and write commands across the interface. But there are some new commands and parameters that we'll get into. So we basically are just trying to extend the usage model and expand it into more markets. So the way we go about achieving these goals is the first concept is these zones. Remember in the drive managed example, we had LBAs being mapped to bands. And now we have bands that are not directly mapped, but the zones are a logical construct again. Bands are physical, tracks are physical, zones are logical. This gives an application a higher level abstractive construct to work with. And it again breaks it up into more manageable pieces. So there's much fewer zones than there would be of bands even in a typical 5, 6, 8, 10 terabyte drive. So all those logical addresses, the zones are then exposed to the host. The host will query the drive and say, how many zones do you have, or what's the recommended usage of those zones? And the drive will communicate that back, and then the application will make a choice and configure which zones, how many zones it's actually going to use during runtime. And then there's the concept of a write pointer. So a write pointer within each zone, when you're writing sequentially, is always explicitly known, and it helps the application and it helps the drive keep track of where the next write is going to go to. So everybody knows that we're writing sequentially and exactly where the next write is going to happen. And then the host controls the zone usage, so it will tell the drive when it wants to evacuate a zone, if a zone is empty, if it's using, if the zone is full. And what we're really trying to do is allow applications to make better use of the capabilities of these SMR drives. So we kind of covered some of this when we talk about bands in the drive managed perspective, and then zones and the host-aware construct. So again, the write pointer zones, we actually refer to them as sequential write preferred, because again, in a host-aware, nothing is absolutely strict or mandatory. If you want to develop towards host-aware and you've only got 20%, 50%, you're only 80% of the way there, then a host-aware drive will still work in your environment just fine. The other 20% of the cases, it'll revert back to the old drive managed way of doing things. And then each zone has its own state, and we'll get into states here. So very, very kind of oversimplification here. A zone can either be empty because it hasn't been written to yet, doesn't have any valid data in it yet. When it has valid data in it, it's considered open. I personally would prefer the term active, but It shows open, and then the last state is full. So you're either empty, it's being written to, or it's full. And this is a way for the host and the drive to keep track of the status of a particular zone, so that the host and the drive can then get ready to start managing, okay, do I need to open another zone? Do I have a zone that's been sitting there with very little data in it? Do I have multiple zones sitting there with very little data in them? Do I need to concatenate all that together, do like some garbage collection, write all that back to the disk into a separate zone, and then I can open these 3 or 4 or 5 zones maybe that only had a little bit of data in them. So the states of the zones are kind of key during runtime. Writes not at the write pointer, this is kind of a key point. Again, like I said, are handled like drive managed. And then when that happens, the write pointer may or may not advance. So again, it's the host, the application, and the drive keeping track of where the application is writing to. And then when you clear a zone or when it becomes full, if you clear it out and you want to reuse it, then you issue a command called reset write pointer, and it resets everything back to the beginning. So the intended usage model, there's a command called report zones. That's how the application would query the drive, or the host would query the drive to find out what kind of drive are you, what kind of zone mapping do you have, what resources do you have available to me. We want you to judiciously assign random write zones as needed. But it turns out that in a host-aware drive, anything can be a random write zone, or anything can be a sequential write zone, or a preferred sequential write zone. We don't have hard restrictions on how those are used. We do have recommendations that say that you shouldn't have more than 16 conventional write zones open at any given time, and we report those kind of numbers as well. So again, the host is able to make decisions on how it wants to run based on the capabilities of the drive. Yeah, I think we covered pretty much all of that. And then just a quick note on garbage collection, which I mentioned earlier. If you have too many random writes and you're filling the disk up with too many small bits of data, either the host or the drive in a host-aware environment can choose to do the garbage collection. The host can do it, or the drive can do it. Okay, so how do we move forward? So there's some things, if you are interested in the technology, you think it would be applicable to your environment, to your workload, to your storage tier. First, we want you to understand your workload, and this is the tricky part, not from your application, but from what the drive is seeing. So you kind of have to understand the application, what it's running on, the whole software stack, the file system interactions, those types of things. And then you have to evaluate how close is what I have to best practices of SMR. How SMR friendly is this environment? Then ask yourself what software resources are available to you. Can you make modifications to the application that are needed to optimally work with a host-aware drive? Are you running either a non-standard file system or a file system where you would have to have resources to make modifications to that? Do you have resources to implement those zone commands, feature and command set as being defined by that T10 and T13 committees, according to the intended usage model? Next step, familiarize yourself with those specs if you have them already. They're freely available up on the T10 and T13 content on the websites. ZBC Rev 2 is in letter ballot review now. And then the ZAC is coming soon right after that, potentially 3 to 6 months. It will start going through the review process. We'd like you to obtain some drive samples and just try it out. You really, in some cases, don't know until you actually do a proof of concept. So some resources that you can access. So we have t10.org, t13.org. There's a GitHub site where Dachi's got some user space libraries out there that you can use for emulation if you don't have access to samples, but you can do your software development, run them against these libraries, and work out any incompatibilities that you have. They do a good job of simulating the functions of the host-aware drives. And then Seagate is announcing today at the Linux Vault conference out in Boston, that we are contributing to Linux open source some ext4 file extension optimizations for Linux. So if you're interested in that, those should be posted on the conference proceedings within maybe a couple days, hopefully by the end of the week. So I encourage you to go check that out as well. So just to summarize, most cost-effective near-term capacity gains really do require SMR. Some applications run well on drive managed. You don't really know until you try it. The whole goal of host aware is to broaden SMR's appeal to a wider range of applications. And then, dig deep, understand your environment, look for where this can be leveraged, and look for opportunities to adopt host aware SMR.
So before we go to questions, just note that there is a demo Ceph with Flash and SMR drives that is outside at the demo zone. So you can go ahead and look at it. So any questions?
You mentioned about the host need to create a read drive about the zone configuration and the specifics. Is the zones information and how they're logically mapped pre-configured per drive type, so they are configurable by the host?
The zones are pre-configured by the host, but how you use them and how you designate them between conventional and write-preferred zones are all dynamically configurable by the host.
But how do they store the information since the drive, the cache will go away, and if they need to write those information into the track, these are not reliable, right? So I mean, do they have kind of like a flash storage in order to store this dynamic information?
No, but there are also rules that it has to do with zones. You have to completely evacuate a zone before you can reconfigure it. You can't just dynamically take a zone that has some valid data in it that hasn't been, or maybe that's in the media cache that hasn't been sent to the drive yet, and then just dynamically reallocate it on the fly. There are still certain kind of sequences and rules that you have to adhere to in order to make that work properly.
Any other questions?
I had a question related to workload. When you described that the indirection system you have will need to replenish itself and do a read modify write on a zone. Have you studied all under the different use cases you're broadening to what the increased or the difference in workload is on the heads of media?
Yeah, we have, but I'm not prepared to discuss that on this. But I would like to make one slight, clarification. The media cache does not really do, when you think about LBA indirection, that's a different concept than a media cache. LBA indirection means that you're writing randomly to the drive, but then the SMR drive would somehow rearrange those and write them sequentially to the disk, right? That's not what we're doing. We're allowing you to randomly write wherever you want, and then this media cache will autonomously do the read modify writes for you within the zone, but ultimately it gets mapped back to the tracks and the bands on the drive. So it's a little bit different of a concept.
So I'd like to take it a slightly different direction. We asked for fully host managed, and when we ask for that, we really mean fully host managed. Fortunately, I don't hear you saying that host managed goes beyond the data layout, but includes all the background tasks that annoy us when you go off and powder your nose without telling us, etc. So can you elaborate on how you're going to fulfill on the even performance that we hope to get out of fully host managed?
All I can say is that all has to do with how you manage the zones and trying to limit the random.
Right. That's the data path, though. You suddenly will disappear and go grease leveling, or a whole bunch of other things that you don't let us have any opportunity to do anything. And the application profile basically gets hit in the kneecaps. And
so it only gets hit in the kneecaps if the cache gets full. And I guess you could say that that's a trade-off of us trying to provide the flexibility of host aware so that people that are trying to get into this space, that want to make use of this technology, host-aware gives you a little bit more flexibility if you don't have the software development resources to take it to the level maybe that you guys are trying to do.
Right, but it's an issue of if I'm going to put an SMR drive into something other than my archive or cold storage, if I'm going to do any kind of data processing on it, I'm going to run it in maybe one of my lower class Hadoop clusters. I'm going to need to be able to get guaranteed response times out of it. So I'm going to basically build my cluster according to those response times. So that includes the non-data path. And are you prepared to talk about the non-data path?
We could have a private conversation about that. There are some architectural enhancements that we're making for future products that I think might address some of those concerns, but I'm not prepared to talk about that at this level.
All right, so thank you very much, Paul.
Yeah.
Our next presenter is. My glasses are full. Amit. Mics for you. So I called it back. We had the same issue yesterday. They had to turn off and on there.
There was a reliability issue.
That's typical. It's typical support when you need them, they're not here.
So just trying to get you number two, but just TMI.
Maybe there's a laptop.
No. Maybe you get started with that. So maybe we can present it. I work on this one.
Shall I start?
Yeah.
You good? All right, so I'm going to talk a little bit about, the overview is essentially about drive reliability and what kind of the best practices are and what mostly determines the reliability of a hard drive. I'm not going to go into SMR and basically handling data at scale. And so just to give some background, I'm part of the advanced reliability engineering team at Mythology in San Jose. So that's kind of the outline of the talk. One of the big problems we're facing right now, this one if you delve into the physics of it, the material science of it, you're essentially trying to control macroscopic objects at nanoscale distances. That is, it's one thing to control nano objects at nano distances. When you try to do something the size of a micron at like a nanometer, it creates problems of its own kind. And kind of what we'll talk about is essentially the critical parameter, what people
what we realized, and hopefully I will show you some data. I will show you some data, hopefully convincing data. The critical parameter is, as we have gained, as we've understood more and more, it is the workload. Okay. So we kind of point out what the historical, limitations of the reliability modeling has been, the importance of workload and temperature. At the very end, kind of give you a little teaser about, field health monitoring systems. Okay. So, from an HDD reliability point of view, what are we trying to do? I mean, the principal goal is always to avoid an unmanageable catastrophe in the middle of the drive's warranty life, or before the drive warranty life. So this is what we refer to as a wear-out mode. Essentially, it means you need to test and be sure to know that you've never hit something like an unbounded failure mode at large times. Okay, that is the primary concern you need to address when you essentially design the reliability into a drive. And the second piece of it will be, for drives that are out in the field, can you do some kind of predictive analysis, let's say, to get a lead time to failures? And the second piece is, can you get me some kind of, as a customer, can we provide the customer some kind of a dashboard for a population of drives? Be it a data center, be it some other environment, but can we do that? So, which is
I can show you, but it's switching.
Thank you. So, we'll go through very quickly through how do you define a product's life, and what are the factors that determine the life of a drive? What are the dominant factors? Again, there are many of them, but we're just focusing on the dominant ones. And how can you, given those facts, how can you help customers perform an effective fleet management? Okay. So again, forget the details of the cartoon. What you want to focus at, I don't know if it's visible at all. If you look at the picture in the bottom, what you'll see is essentially, when I say clearance, it's the distance between the head and the media of the drive. And as you keep going lower and lower, by the time you hit something like, for example, a 2 nanometer average clearance, your tribology problems, the head coming in touch with the media problems, just completely explode and start dominating your failure grids. Okay? So most of the failures you see in the field is because I cannot keep my head steadily over a media because of reasons of physics and chemistry and material science. And that's where they start dominating. Okay? So if I went back like 3 generations or 4 generations, when I was flying at like 4 nanometers, it was much less of a problem. And it has to do with, for example, anomalous physical phenomena in ultra-thin films. I mean, you go beyond a certain amount of film thickness. The physical phenomena that are driving the unreliability modes, if you wish, start changing. Okay, and you have nonlinear response functions of adhesive and frictional forces, and so on and so forth. Okay. Now, again, this is kind of it gives you an idea. These are, HDDs are, again, complex devices that push the envelope of our physics understanding in a various number of areas. For instance, just to give you an idea, you sort of, this we know from thin film physics. If you start stacking up various layers of thin films, you kind of go to a region where, how the layers keep forming on each other in the media, for example, the loop layers. There's a certain kind of terracing that happens, and you start fractalizing. Okay. Now, what that will do is, and it sounds very academic, but it really isn't, because that profoundly impacts how your air-bearing surface is going to talk to the media, depending on the loop thickness. Okay. Whether it adheres, how much it adheres, when does it, what temperature range does it not adhere in, and so on and so forth. So it becomes a very, very delicate balancing game. And the reason I'm mentioning all of this is because you're operating at a distance which is basically the size of a couple of carbon atoms, these little details, whether it's 1 layer or 2 layers, matters a great deal. Okay. And that essentially transforms into, what the reliability risk that's being posed to the hard drive. Okay? So you have that. You also have things like, for example, from a, both the head and the disk have something, they have a protective layer on the top. They're essentially, they're called DLCs, diamond like carbon. And what you happen is, what could also happen, and we've seen this happen in terms of the returns that come back to the field, and it's an industry-wide problem. You basically have a carbon that's 2 nanometers. Now, depending on the usage condition of the drive, what will happen is you will start leaking. For example, the magnetic layer in the media has cobalt, and it will start leaking out. Okay, there's a cobalt leaching problem that can happen. Essentially, you kind of migrate through the carbon and start collecting on the top surface of the media, like I show in the picture over here. Now, when you have a very high kind of workload situation, you start collecting this on top of the head. So that's a magnetic, that's a reader, that's a writer. You start smearing it with cobalt. Okay. So environmental conditions, so depending on very little details of how exactly the carbon bonding is, ratio of sp3, sp2, and so on and so forth, you could either have things like this, or you have the head coming in contact in the media, and you start wearing out. And this is the head carbon. If everything was okay, there would be kind of a gray, outline. What you see, this whitish area, that's where the carbon is being worn from the head. So essentially, what I'm, and all of this happens because we are trying to manage, again, the head media distance, the head media spacing, to a nanometer level. Now, how does this transform into, what does this mean in terms of how the hard drive should be used or shouldn't be used, or in terms of reliability? Okay, so let's kind of quickly go through what the classical reliability model essentially gives you. It is a bathtub curve, okay, where in the initial stage of a drive, you have an infant mortality region. Okay, that's the first piece of the piece of the curve, where your failure rate is actually coming down with time. So this happens because the system is essentially, there are defects, there are quality escapes, and marginal materials, and so on. So it's essentially purging the initial bad material from the system. Then you go into a steady state of failure in the middle region, where you've taken care of all the initial bad materials and stuff, and then you have a fairly steady state of failure. As you can see, the failure rate is failure probability is fairly steady, and that's where you want to be during the entire life of the drive. What happens is, if there's an intrinsic problem or other reasons which I'll come to in a second, if the drive is taken beyond its capability, that's where you start having a wear out, where your failure rate starts increasing with time. And what you want to do is absolutely stay away from this, because once you get into this runaway situation, you can show it by modeling, that it essentially becomes uncontrolled. Okay, so, and the reason why it becomes uncontrolled is little changes in the slope of this curve can take you in between failure rates that are like 5x apart from each other. So you can fail at a 5% rate, or you can fail at 30% rate, depending on how that curve is flexing. So you absolutely do not want to go there. Okay, that's basically the reliability. That's what needs to be baked into the design and the usage, so you do not hit that red region. Now, historically, what happens in terms of time evolution of a failure rate or unreliability, whatever you want to call it, it was modeled as a function of time. You had a function that's f of t, and it was it goes like an exponential. It has certain constant beta, eta, and so on. But basically, that time was interpreted as a power on hour of the drive. Okay, so basically, as the power on hours, the more the drive is powered on, your failure rate would go up with time, up to a certain power. Okay? So it would normally be something like this. So if you look at the cumulative failures versus days in field or power on hours, however you interpret this, there would be a failure rate that scaled like this, and you know how much power on hour, how much you're powering on the drive on an annual basis, and you say, okay, that's 1 hour, 1 year, that's my failure rate, 2 years, that's my failure rate. It's a saturating failure rate, okay? And that would give you a mean time to failure. The mean time to failure traditionally is what was spec'd for a hard drive. And that is given by the time required to fail 63% of drives. Basically, you take the exponential to the power of 1. But what I'm going to show you, though, that by itself, the traditional mean time to failure essentially means very little. Now, okay, the other important aspect, so the time was one piece of it. The other aspect of this was temperature. Essentially, you take a hard drive and heat it up. You go to a hot environment. If you stay at kind of ambient-ish environment of 30°C and so on, you have a low failure rate. As you keep heating up the drive, the failure rate kind of scales up the temperature. And there are various people who have, the study has been done with all the major players in the hard drive industry, and you kind of have a sense, okay, if I operate every 15 degrees, I'm roughly doubling the failure rate of a hard drive. Okay? And you can kind of, we have enough data to show that that's typically true for most failure rates. It follows an equation called the Arrhenius equation. Now, so that's the temperature piece of it. And the previous thing I said, so historically we would have this power on hour and this temperature determine what the health of a hard drive is, what the failure probability is. Now, if you take the same thing, another interesting thing is if you go to low temperatures, you get an entirely different set of problems, and the failure rate starts going up again. So what you see in terms of temperature, it will be the best behaved, let's say between, 5°C and 30°C. If you go on either side of it, you have different physical phenomena, but the failure rate keeps going up on both sides. With a slightly different exponent, but it goes up on both sides. So that gives you a sweet spot of where a hard drive should be used, temperature-wise. Okay? So, and you want to avoid this, the two temperature ranges. And this is a list of things that you typically run. Again, a whole host of things that happen, both of the temperatures, if you go beyond these operating ranges. And the risks at hot and risks at cold are somewhat different, but they're risky in any case. Okay? Now you can design for a high temperature application, but you have some trade-offs that are associated. For example, in an automobile, you use a hard drive in a car. It will be hotter, but you do certain trade-offs when you do that. Okay? Which will basically take this curve and flatten it out at a high temperature. Now, historically, what is happening in, as I was saying a little while ago, you had a temperature, you had a power on hour in that equation, and you had a duty cycle. And we would typically, all our drive vendors would basically give you a duty cycle, like everything was 100% duty cycle. Now what we think is that's a fairly useless thing to say. A duty cycle doesn't really mean anything. Okay? For example, I take one drive, and a whole population, let's say 1,000 drives. Each of these lines correspond to 1,000 drives each. And I run them at very different workloads. Okay? One is having 120 gig per hour, one is 180 gig per hour. And they're on the whole time. So it's both are 100% duty cycle in that sense. If you look at the cumulative failure rate, what you will see is there's vastly different, I haven't put numbers here, but they're vastly different numbers. They were 50% higher for the higher workload. So if I took that chart and made a log plot out of it, I basically get a straight line. Okay, and the slope of the log line is an exponent that gives you the curvature of these two curves, which is 0.8. But what you see, however, is if I take the blue line and say, okay, I'm going to define my MTTF when it hits a certain failure. So that's log of failure. This is log of time. And I put a metric there and say, okay, when is the blue line hitting this? And that's what defines MTTF of the blue population. What you'll see is the blue and the red will give you two different MTTFs. So it's the same hard drive, exactly the same thing, same duty cycle, two different workloads, give you two different mean time to failures. So speccing mean time to failure by itself is simply not a very useful, metric. It's an insufficient measure. What you do instead is you scale it with the total terabyte transfer. And when you do that, what you find is these two curves, when instead of the power on hour on the x-axis, you plot it as terabyte transfer, which is workload times the power on out, they will start collapsing on one single curve. It becomes kind of, they start belonging to the same universality class, if you wish. And that defines exactly what the health of the drive is, or what it should be spec'd at. Okay? So instead of a mean time to failure, you start talking about mean petabytes to failure. Okay? So that becomes a natural reliability metric, and it kind of leads to, if you wish, from a data center management point of view, you want to have, it's like a drive workload monitor would be a good thing to have, because that tells you where you are in that curve and what you expect your failure rate to be. It's essentially the workload will define this. And I think at this point of time, pretty much all the HDD manufacturers are speccing the workload on their drive. And this is the reason, if you wish, why it's being done. It's a critical driver of HDD reliability, and it's a very quantitative thing. You can read it off of logs. We have the total amount of data transfer, which is sectors written and read, and that tells you exactly what your failure rate should be. And again, the best units are terabytes per year. So just to give you some typical numbers from WD drives that we use, for example, these are from field usage specs. You can start figuring out, okay, what is the typical usage of these various swim lanes? And you can see a nearline enterprise will be about 550 terabytes per year. That's what our RE drives are spec'd at. And you go down, so compared to a typical desktop drive, it's about 10 times more. Okay, so using a desktop drive in an RE environment, you should be, one should be willing to accept about a 4 times higher failure rates. It's going to be the factor of 10 to the power 0.6 or something. So it's 4 to 5 times higher failure rate by using that in an RE environment. I'm going to close up because I know we have a hard stop at 2. So the last thing I want to hit is, I'm sorry that it's being chopped off at the top. Now, this is a capability under development. This is WD's SelfMonitor for a class of drives, for a population of drives. So it provides a potential to, it can provide kind of a real-time health dashboard. And beyond just going, beyond just an overall dashboard, you can identify poorly performing drives or heads before actual failure, so appropriate actions can be taken. So the end result is going to be you assign kind of a health index to each drive as a function of workload, other environmental factors, all of that kind of compiled together. You assign a health index to each drive at any given slice of point of time, which is going to be seen by the consumer. It will allow you to do what one calls drive-less FA. So you know why that hard drive is suffering, you can isolate the cause. I'm not saying it's not going to heal it, but it's going to at least isolate the cause of it. And it enables a closed loop eventually. You monitor, analyze, predict, act, and so on. For this SelfMonitor, we have done a fair amount of work in internal benchmarking. It's not, the public domain yet. And we have about 2+ years of experience in doing internal benchmarking. And the natural progression will be kind of put in the user environment at some point. So to give you an idea of what this in-field health monitoring system does, is essentially stores a bunch of critical parameters throughout the drive lifetime. So there's live data coming from each drive. And you output a relative health index. Okay? So if you think of this is kind of a chart that shows the health index. This is the population of, there's not very many drives, but we've done it for like at least 2 orders of magnitude more drives. So about 2,500 drives or 2,100 drives. And you see most of the drives essentially will remain healthy. So this is the big skyscraper is a healthy end, okay? And what you see, you have a health index that starts at, let's say, 100 and kind of depletes as the drive weakens, if you wish. So when it's really, really healthy, you have this is a real failure rate under internal testing. It's low. Now for the drives that are weaker, you essentially have, so you go for failure rate of, 3% in this particular case. For the worst drives, you isolate, they're like 85% failure rate. Okay? So, and this will allow you to know, this is kind of a dashboard, it can be fancied up, but that's the rough idea. Okay, you go from a high, so all drives, when you leave this door, you kind of, you're at this end of the population. As it continues, you kind of, start populating this part of the curve, and you know which ones are the weak ones, and take appropriate action. Okay? Low score is bad, high score is good, blah, blah, blah. So it'll be equivalent of a gas gauge, if you say. Okay, I think, you know, that's, so this will kind of eventually, again, this is an internal, you know, capability study that's going on right now. And one can match this with various amount of things like SMART and other workload monitors to effectively overcome the shortcoming of that we currently have in many predictive models, predictive tools. And you know, that's it.
Great. So any questions? Oh, one.
Mark Hall, Seagate. Do you see any of this moving into an open community? A lot of people have a lot of ideas, and I'm involved with some of this in Seagate on the fringes. But it seems like things could go much faster if it was a lot of people working together.
I would probably agree with that, yes. And I think I was talking to her over lunch, and yes, I think that's an aspirational goal, shall we say. Whether we get there or not.
Would you support having a subcommittee from this working group? Well, I bring it up today. But we support the idea of creating subgroups so you have software that makes it from the community. What we would want is a dashboard we plug into the type of drive. And certain features you feel that you know what you're in are, and I'd rather not. Would you support it? Anybody else here? Any questions? Okay. All right, I'll put it up for the mailing list and get it a working group.
I was just curious, you talk about I/O specifically, throughput, but is there any impact on this relative to randomness or sequentialism?
No, there isn't.
No.
No, it doesn't matter what you do, all that matters is how much you do. To first order. Again, there are going to be specific cases with a little deviation, but the first order is always how much you do that is used most.
What is the difference between a high usage drive, enterprise class drive, say 500 terabyte per year, versus a desktop 50 physically, or if something has changed that allows?
Well, yeah, exactly. I mean, a few things, I mean, some of this is obviously proprietary. The first order you can think of it, most enterprise drive will have more data points. So you divide the workload equally. To get to the same workload, let's say you have used 10 heads to get to that final workload, versus 2 heads in desktop to get to it. So, and there are other tricks one would play. But to answer your question, if I take the same heads and have 10 of them, so 550 terabytes per year, if I split it over 10 heads, that's 55 terabytes. Whereas I did it over 2 heads, it would be get hit. Each head would get hit much more. Okay, and you can look at head level failure rate, and you can compute it out. So that's the primary difference. You mean the ladder count is the same, or the actual? No, there are differences, of course. Yeah,
And just as a quick comment, pair with what you were suggesting, this is Dan Reno of HDST. We'd also welcome trying to look at it, as you stated, pair from, how do we allow it from a dashboard and in terms of, doing the whole health monitoring. So good idea.
So with that, thank you very much.
Thank you.
So when we designed Knox, we spent a huge amount of effort on RV isolation. So there, Knox's connectors didn't float, and the drives are only self-induced RV. You didn't say anything about external conditions that cause failure.
I did not. That's correct.
What effect does that really have, and did we waste our time?
I could make it an offline conversation. Yes, there is an impact. Okay, but here I was focusing on what we see is, if you take an aggregate of the drives that go out in the field, what you'll see is this is by far the biggest hitter. They may not cause individual hot sites, for lack of a better term, but this overall workload dominates. The workload-driven failure modes dominate your failure pressure partners.
And so as long as I stayed within power ups and power downs and unloads and so on, I could have a cold storage box that lasted 20 years. Because I wrote it once and I read it hardly ever. The thing should be perfectly fine. I may have to put some wax over the hole because I have humidity problems, but
That's how you want to see it.
that's the message you're delivering, right?
To some extent, but again, I mean, obviously with cold storage drives, they're also spec'd differently. I mean, they're,
Well,
there's a reason why they're spec'd differently.
Yeah, that's because you guys wanted to.
So,
I wanted it better.
yeah, exactly. So for cold storage, for example, you do need to worry about, as you said, how often you access the data and how long is that, is the quiescent condition versus, active condition and so on. So the other factor, as I said, this is kind of the first order effect, but for each swim lane, you need to start tweaking it a little bit and getting it right. But for this was mostly kind of already,
Yep.
Yeah.
And so next year when you come here, you're going to show me what all those swim lanes are and their total effect, so we can start doing math.
We can do that, yes.
Thank you very much. Again, all the presentations will be uploaded to the Wiki site. And with that, I think they are expecting us upstairs. Thank you.